ladies and gentlemen, and welcome to Proctor Lecture, sponsored by TC202. This is Chung Sik-kyu, and I am privileged to chair this lecture. As I mentioned, this lecture is sponsored by TC202, Transportation Geotechnics, which was previously TC3, Geotechnics for Pavement. I'd like to invite TC Chair, Professor Errol Tutum-Luer, for the introduction of the speaker. Errol, please.
Thank you, and good afternoon, everyone. I would like to first start talking about TC202 and its goal. TC202, known as Transportation Geotechnics, has the goal to apply broad engineering to bridge the gap between pavement/railway engineering and geotechnical engineering. So with this main task in mind, our goal is to again promote cooperation, exchange of information and knowledge about the geotechnical aspects of design, construction, maintenance, and monitoring and upgrading of roads and railways, as well as airfields. The Proctor Lecture was first established during the last International Conference on Soil Mechanics and Geotechnical Engineering in Paris in 2013 to commemorate significant contributions of late Ralph Roscoe Proctor and to be delivered by world's most distinguished achievers in transportation geotechnics. Ralph Proctor was an American civil engineer, well known as the inventor of the Proctor test and the associated theory of compaction. So this memorial honor lecture is organized as the primary keynote event at each Transportation Geotechnics Conference hosted by ISSMG's TC202. The first Proctor Lecture was delivered by Professor Budima Indiraratna of University of Wollongong during the third International Conference on Transportation Geotechnics in 2016. This is going to be the second Proctor Lecture to be presented here today. And it's indeed my privilege and distinct honor here to introduce to you the founding member and our immediate past chair of TC202, Professor Antonio Gomes Correa of University of Minho, Portugal, who will present the lecture entitled From Fundamentals to Applications in Compaction, Recent Developments in Embankments and Structural Layers of Pavement and Railways. With that, I would like to also say a few words about Professor Antonio Gomes Correa. He's actually, as you know, from Portugal. He received his PhD degrees from EMPC Paris Tech, as well as Technical University of Lisbon. He worked as a specialist at the National Laboratory of Civil Engineering and as a professor at the Technical University of Lisbon. Since 2003, he has been a full professor of civil engineering at the University of Minho, where he has served as the Vice Dean of School of Engineering since 2013. As the chairman mentioned, Professor Gomes Correa served as the chairman of the ISSMG's European Technical Committee, ETC11, on geotechnical aspects in design and construction of pavements and railroad track. This was from 1998 to 2001. In 2001, he became the chairman of TC3 of ISSMG's on geotechnics for pavements, which was named or renamed actually in 2009 as TC202 Transportation Geotechnics, and he's been the immediate past chairman of TC202 then until 2013. Professor Gomes Correa has been involved in research, teaching, and consulting in the general field of geotechnics and pavement engineering for 38 years. His work embraced transportation geotechnics, particularly soil and pavement geomaterial properties and modeling, compaction, which he's going to talk about today, soil improvement, foundations, and geotechnical design and management. He has over 400 technical papers and 240 reports published on these subjects. He supervised over 100 graduate students, about almost 33 being PhD students, and he is also the editor-in-chief of the International Journal on Transportation Geotechnics, published by Elsevier since 2013. Please join me in congratulating, or join me in actually welcoming, rather, Professor Gomes Correa to present his lecture.
Thank you, Chairman, and is my great honor to be invited by the TC 202 Transportation Geotechnics to deliver this second Proctor Lecture. It was difficult to choose a title for this lecture, and finally I decided to choose this title, From Fundamentals to Applications in Compaction, Recent Developments in Embankments and Structural Layers of Pavements and Railways. My topic will cover starting from the historical part, the past, and going to the present and to the future, showing the developments in embankments and the developments in structural layers, mainly with stabilized soils, with unbound granular materials, mainly, and also I will touch at the end a little about the ballast, because I intend to cover the road and the pavement and also the railways. And some final remarks. As has been mentioned, Proctor was an engineer in the field, and he developed during the construction and post-failure of San Francisco Dam the Proctor test, and in fact he got the very known name from 1933, when this test was established, and mainly when he did the 4 papers presented at the Second International Conference of Soil Mechanics and Geotechnical Engineering in Rotterdam. And I just want to mention that one of these papers was not related with compaction, but was related with elimination of hydrostatic upflow pressure in new earth fill dams, and it was considered one of the pioneering papers on this subject. So Proctor was a practical engineer in the field. So I was thinking to give the direction of my lecture in this way. So connecting laboratory with field and technologies. This is my approach. I just go very quickly to some historical data. So, as I mentioned, one of the papers presented at the second conference, International Conference of Soil Mechanics, was this one, Fundamental Principles of Soil Compaction. And this was presented as an alternative method to the California test 216. And this California test 216 was established by Proctor, that was, by the way, the author of the introducing of the Californian bearing ratio, CBR, that everybody knows in pavement engineering. And this test was proposed to evaluate the load bearing capacity of pavement subgrades and aggregate-based courses by comparing the penetration resistance of these materials with that of the crushed limestone. Here's some pictures from the past, how it was the horse scrapers, the damping wagons, how it was compacted for high embankments. The material was followed on. For that purpose, you have to construct a structure in wood in order to fall down the material, as you can see here in the picture. And then you have probably the first sheet foot roller in 1902, and after, when the mechanical engineer take place from 1930 to 1940s, they appear the first mechanical equipment for earthworks. I cannot let to mention McAdam, sorry, because it was the one that introduced the granular layers for the pavements. And here you have the 5-tone limestone roller used to compact the crushed limestone and river gravels, exactly using the first principles advanced by McAdam in 1916. Then you have also for historical data in 1946 the introduction of the modified Proctor bases. And here you have a picture of the first domestic airport runway designed using the new design methodologies employing this modified Proctor compaction. The TC, actually the TC202 that became from the European Community ETC 11 have done from that time a lot of work related with compaction. I must say that the first important event was during the workshop in the Intermat 2000 in Paris. We published then this book by Compaction of Soils and Granular Materials by the press of École de Ponts et Chaussées. And then we have another important book dealing with the subject that was done by myself and also Hans Brandl, compiling a series of very nice papers related with earth structures. And another one that was, by the way, the first one where we propose a draft for a standard related with the roller integrated continuous compaction control prepared by Dietmar Adam, and this was, as you can see here, published in 2005. And we have also promoting some webinars related with intelligent compaction, some papers and keynote lectures in this subject. This is the last webinar done in the Center for Advanced Infrastructures and Transportation in El Paso in 2015. And now moving to the fundamentals. Everybody knows how these curves of compaction were prepared, putting the dry density with the water content, and you have the standard Proctor and the modified Proctor, and by the way, this California test is somehow in the middle. Also, you can see that the soils have different curves. The clays are generally with low maximum dry density and high optimum water content, and the granular soils are lower optimum water content and high dry density. And there is a very interesting paper proposing, based in 20,000 tests, this family of curves related with compaction of soils. You will see that these curves were used later for Professor Tatsuoka to propose a methodology for the use of the compaction in the field. So the compaction, as you know, is applied to the soil to find the optimum water content that maximizes its dry density. The main objective is to decrease the compressibility, to increase the shear strength and the stiffness, and in some cases reduce the permeability in the purpose that we will design properly the structures for durability and stability. There are a lot of papers and studies trying to explain the shape of these curves. Others are trying to reproduce this compaction curves. I will not go through because I don't have time. And in this context of compaction soils, there are recently the introduction of the microstructure when it becomes very easy to measure the pores in the soil, introducing a microstructure quantified by a state variable, and apparently, according to the authors, it opens the way for a systematic evaluation of microstructural effects on measurable macroscopic engineered variables, such elastic stiffness, strength compressibility, yielding behavior, and permeability. So, going now to the embankments, the important aspects for the design may be considered in 2 points of view. The structural design, and this is generally treated by the Eurocode 7 and 8 or other rules, specifically in the case of dams, and the execution, that it means how to build to obtain the need properties. And we have actually, going on in Europe, the standards prepared by the Technical Committee 396 related with earthworks. This is really very important, more even in railways, because as you know, we are much more restricted related with the service state limit for railways than we are for roads. The structural design check, as everybody knows, the stability, the formations, and the hydraulic behavior of the complex structure and its foundation. The mechanical and hydraulic properties assumed for design should be compatible with material and construction procedures. So it's very important that we look to the construction procedures and the control method in order to be sure that these properties obtained for design related with the durability and the safety of the structure will be assured. So in this purpose, this European standard related with earthworks allows the use of different types of materials in order to construct the embankments. And this is very interesting because you can do really the management of the materials available in the field. As you know, more and more, we want zero material in the construction of the embankments by environment reasons. So we try in this way to accommodate or treated materials in order to have the use of them coming from the excavations. So here are the possibilities for the foundation, for the core, for the shells, for the transition zone, for the capping layers, and then for the structure, never mind if it is for pavement or if it is for rail tracks. But the important thing that is mentioned in this standard is that you have to, of course, do the study in the laboratory, but this study should be validated in the field. So there is always a link between laboratory and the field to be assured in the work. So related with this, we tried from the compaction curve to identify the properties related with design. And recently, Professor Tatsuoka proposed, or he noticed from this family of curves that I showed you before, that in fact, if you put these curves using the dry density under the maximum dry density and the degree of saturation in relation to the optimum degree of saturation obtained at the maximum dry density, then you can more or less assemble all the family of compaction curves. This is an important statement because it shows that apparently using these parameters and mainly using the degree of saturation, you can, in that case, avoid the energy of compaction of these curves. And here is the proposal that we should use for design. In the past, it was very common, as you can see here, by Mitchell in 1965, to define the range where we can work between a minimum water content and a maximum water content related with the optimum water content for a certain work. And what is proposed now, because of these findings related with the degree of saturation, is not use the minimum water content, this range between the minimum and the maximum water content allowed in the field, but use for the point in the field of the compaction the degree of saturation line, and if possible, you should work with the degree of saturation at the maximum density. So, in fact, there is a change in the philosophy for the field. In behalf to use the minimum water content, you should choose a degree of saturation as the lower bound of your compaction state for the work. So this is something to be developed. If you are interested to learn more about this, you can attend the TC202 workshop on Thursday. So for the construction, you have nowadays an important development related with the intelligent compaction and the integrated monitoring of the compaction. This, as I mentioned, it was established in 2005, the first draft to deal with this. And as these equipments have the possibility to know the position where they are and register the acceleration of the interaction between the roller, the drum, and the soil, you can find a kind of parameter related with stiffness in continuous of the compaction. So at the end, you can get what you find before when you start the compaction. So there are weak zones in the beginning of the compaction, and you can see what you will achieve at the end of the compaction. And this with 100% of coverage of the compacted area. This is really a very important achievement that is nowadays available, and there is a lot of projects going on in this, mainly in the United States. I will refer this later on. We did an experimental test in Portugal for the demonstration of the advantage using the intelligent compaction that have, of course, the capacity to continuous monitoring the stiffness of the compacted layer. But just to show you, we use two compactors, one vibrator compactor, a classical one, classified as a V5, and another, an intelligent compactor, classified as a V4. And you can see that the intelligent compaction reach much higher compaction than the classical one, even if it is with more energy applied by the same parameters of vibration. The advantage of the intelligent compaction is that it can change these parameters during the reaction if fill of the roller with the soil. For the control, we have different methods of specification. The method specification, the end product specification, and the performance specification. In the end product specification, the designer specify the degree of compaction necessary under a range of water content, or more recently, under a certain degree of saturation for the given material by reference to a criteria linking to either serviceability or limit states. In fact, the big advantage of this equipment is that you can get a modulus coming from the vibration of the drum interacting with the soil, and you have in that way a performance parameter that can be related with the design. There is an interesting study done in El Paso by Professor Soel, that is here, using different devices for measurement of water content and density, and also some plate load tests using the GeoGauge, the lightweight deflatometer, and the portable seismic property analysis, and he compared the data obtained with these tests, and he concluded that, in fact, for the stiffness, the Zorn lightweight deflatometer was the one that was more accurate. We did in Portugal a trial independently of this study of the El Paso, using also different equipments of compaction. The material was a clay sand covering water -4 to water, optimum water content +2, and also well-graved gravel with the water content -2 in relation to optimum and to the optimum water content. And we conclude the following. For this experiment, it was seen correlation between the static plate load test and the potentiometer, that is also a continuous compaction measurement, but using a standard roller developed by the laboratories of Pons et Chaussée, close to UNIT, so it fits very well in terms of the results of the static plate load test. We find also a very good correlation between this static plate load test and the lightweight deflatometer, and we find a big dispersion or a big scatter with the GeoGauge. What it was corroborating exactly the study done by El Paso with the same kind of equipment to obtain the stiffness. And we were very happy because, in fact, when we compare the models obtained by shiver waves in the laboratory and in the field, we find really a very good approach for both results. The developments that I was mentioned before related with intelligent compaction is one project going on at the National Cooperative Highway Research Program to evaluate mechanical properties of earth materials during intelligent compaction. The coordinator is Professor Sohail Nazarian, and with this project we intend to have optimal approach to simulate proof mapping using finite element method single and two-layer geosystem. So this is a big advance in the intelligent compaction, because you can get directly during the compaction the stiffness of the layer, if you are just compacting, for instance, a subgrade, or of the granular layer and the subgrade. This is really a very big advance for the knowledge relating the field with performance-based parameters with the design. Another project also ongoing is this one, validation of intelligent compaction to characterize pavement foundation material mechanical properties, led by Professor Errol Tuller, is the Illinois Tollway Research Project, and they are intending to validate the results of the intelligent compaction by using the equipment traditional in control, but spot tests to obtain the stiffness. I think that important thing, I will go very quickly because the time is going, is that with these field equipments and monitoring, you are getting a huge data. And the soft computing, data mining, becomes really a very important tool. Not just to deal with this big data obtained in the field, but also to use the data that you have in the laboratory in order to retrieve this data, this historical data, or to predict parameters, or even to learn knowledge with the existing data. So this is quite an important tool. This data mining was not new. It was more or less state of art was done by David Toll in 1996, related with different application in geotechnics. And you can see here what I said before. You can reproduce the volume of compacted material very well with a very high correlation, and also the thickness of the layer multiplied by the speed of compactor. And this is what is in fact assembling all the data existing in the Guide des terrassements routiers in France. We push these things a little further, and we develop, one of my PhD students developed an integrated system for earthworks, which the advantage is to get the equipment, optimize the equipment during construction in order to save time and costs. And so this is really a challenge. If you want to know more about this, you can attend the first International Intelligent Construction Technology Group conference that will be starting on 26 in Minneapolis in the United States. Let's go very quickly to soil stabilization. You can see the past and the present in equipment. And we can use this data mining to learn about a lot of tests that we have done in laboratory with different type of soils, just to show you that one of the parameters very important in the prediction of stiffness and strength is the porosity of the material. Again, one of the parameters of compaction is appearing as one of the most important in the prediction of the stiffness and the strength. Another important aspect is related with unbound granular materials. We are compacting unbound granular materials of different grain size, and what we were looking for is, we know very well the relationship between the void ratio and the influence of void ratio in the stiffness, and we would like to have a general law to predict the stiffness for different grading curves of granular materials. So we did a quite huge laboratory program, a cycle load program. In the loading the material and during the unload, we do different small cycles to obtain the stiffness of the material. And you can see here for one of the materials, the use of the Hardin-Richer function for the void ratio that is very known and used in practice, okay? And you can also see another one used by Lopresti that put the void ratio to a power. And it can be seen between the two laws this one and this one, that this fits much better than the previous one proposed by Hardin and Richards, in fact, more for granular sands. And here you can see what we find. In fact, we developed the equation integrating the coefficient of uniformity. And then we are able, as you can see here, to predict very well the stiffness, or at least the function of the void ratio, to obtain the stiffness of the material for different grading sites with different uniformity coefficients. And you can see that for very dense materials, you cannot use the Richard Hardin proposal. You usually use it for sands. So this is a very interesting conclusion. And if you want to interpret the results in the field, because you have a scatter in the void ratio during the field, and if you want to compare these results with the laboratory, you have here a proposal to normalize the values for a reference void ratio in the field or in the laboratory. Another important aspect is related with the influence of the compaction condition in the stiffness and the permanent deformation of the material. As you know, if we are looking for the pavement for a granular layer, the two performance parameters more important is the stiffness and the permanent deformation under cycle loads. So if I put a scale using the scant modulus and the permanent deformation, you can see generally this is what happened, that the permanent deformation will increase with the increase of water content, and the stiffness will decrease with the increase of water content. We did a study, it was the work of PhD student Coronado in cooperation with Bernardo Caicedo, Taibi, myself, and Floro. And we find a very interesting conclusion is that you can have this, I will say, performance behavior of the material, putting the scant modulus and the permanent deformation, and you can see here how the material can evolve when there is the increase of water content. And you can see two trends. One for the material study from Colombia, that is from the same geological origin. It was orthoquartzitic sandstone, and here that is a reference material used in pavement construction in France, that is the hard limestone from Marshers. So apparently, we could probably do the approach that if the material have the same geological origin, it follow the same trend in terms of performance related with stiffness and permanent deformation to cycle loads. So this is a very important statement for design. Another thing we have here before, Professor Fredlung, is if we know the variation of the models with water content, and we know the characteristic curve, we can, in that case, express the stiffness or the modulus in function of the suction. And using an approach in terms of effective stress developed by Taibi, you can see if you express the vertical stress in terms of effective stress, you get a very good fitting of all the material tests for different water contents, dry, wet, side, compared with the reference material that was the material in the dry side. I am approaching the end of my presentation. Another topic that I would like to cover, because it's really interesting, is the ballast stabilization methods and how you can save time and costs, of course, using them approach modeling to study this in modeling before you go to the field to do some experiments. There is a very nice work done in a team at SNCF in France, and they compare the natural stabilization. What is the natural stabilization ballast? Is to cycle vertical loads to the sleepers for a given time. You can consider this as a dynamic uniaxial loading test on a sample. They compare with another method, that is dynamic stabilization, where the rails are vibrated laterally and applying a vertical load. And this is like a biaxial loading, and a new technique that is studying and proposed, that is the crib compaction, is a direct vertical packing of the ballast located between the sleepers and the shoulders of the track, as you can see here. You have here the sleepers, and you have here the applying of the vibration between the sleepers and in the shoulders. And you find very interesting results, relative results, that can help to, for instance, establish experimental sites to check which solution can work better. So this, I think, is really very important and a very help modeling tool for the ballast. And I came to my final remarks saying that the compaction parameters are K-index properties that continue to be used, but we know and we should establish the relation with the performance-based properties, and by this we can predict the Earth's structure performance. So we can, if we have, as I mentioned after, an integrate chain, if you have the characterization during compaction and you obtain the design parameters, you can check the design and then you can get the performance of the structure. So this is something that should be done more, and I think that coupling the numerical modeling in the laboratory tests and the field tests to analyze the results, as I mentioned for the intelligent compaction in the work being done in El Paso, I think that is a step forward to get this link between modeling and test results. The intelligent compaction for earthworks and structural layers can provide quality control over 100% of the compacted materials and link performance-based properties with the design. Soft computing in geotechnics is an add tool to deal with big data, laboratory, field, monitoring, retrieve existing data, predict and discover, and also to do the optimization, as I mentioned before, in this integrated system that we develop in order to being a helping decision-making tool available for the engineers. And I think that here, the Joint Technical Committee too can have a good participation putting these things to application. We have in academia a lot of knowledge about these expert systems, but the link with the industry in geotechnics is still very small. In opposition, what happens with medicine, because these tools are very used nowadays with medicine. The discrete element method in simulating the particulate materials like ballast is a powerful tool to help in many laboratories and field parameter studies solution, saving time and costing. So is also a very important helping decision-making tool. And I will say that the Proctor Lecture, it was a decision of the committee, will be published, all the Proctor Lecture, in the Transportation Geotechnics Journal, and this lecture will be available following the address of our president in open access in the volume of March of the Transportation Geotechnics Journal. And with this, thank you very much for your kind attention.
Thank you, Professor Correa.